This video is going to cover axial deformation. So the axial deformation equation is not anything new because we've already learned that the modulus of elasticity is equal to stress over strain. We also know that stress is equal to the load over the area, and we also know that strain is equal to the deformation over the original length. So all axial deformation actually is just trying to find that deformation over here, but in a little bit easier way without having to kind of jump through hoops with these equations. So effectively it boils down to just P times L over A times E. So again, P, axial load, divided by area. That's area that's perpendicular to the force, right? Because this is a normal force for axial normal deformation. L is the original length, because again, that's the original length that you see over here. And E is again modulus of elasticity. So this isn't really anything new. This is just us throwing it together in ways that'll be just slightly different. So the only thing that we've got to do this time is to find, say, total deformation. Total deformation is when you have obviously more than one piece, more than one area, more than one material, more than one load. Anything that could be changing any one of these particular variables that we have in this equation is going to need a different little segment to calculate for deformation. And then to get total, if you want to sum it all up together, then what we need to do is draw an axial force diagram chart, right? Because that's really important. So if you have changing load, you need to do an axial force diagram. If not, you're going to find the deflection or the deformation for each segment. And again, a segment is when you separate out a different material, a different cross-sectional area, or just, again, could be change in load. Or something could be of a different length, though again, if it's in a different length, it probably also is a different material or a change in load, that kind of thing. So you have multiple reasons why you could do that. And then step 3 is to sum them all up. But when you do sum them, kind of important to note that you do need to pay attention to signs. Because not all things are going to be positive, not all things are going to be negative. Sometimes you'll have, axial force that's in tension that'll create positive deformation. Other times you'll have something in contraction. So you definitely want to have, your signs for positives and negatives included in your summation equation. Don't just sum up all the magnitudes. It's not really going to work. So just pay attention to that. So in order to do this, we're going to experience a whole bunch of different things going on at the same time. For this example, I've got a pretty terrible drawing, but we have 3 rods all connected together. We have an aluminum rod that has a distance. It'd be really good to know the distance, right? The distance of the aluminum one is 1.5 feet. The distance of the brass one, 2 feet. The distance of the copper one, 3 feet. We do have some forces, as you can see, the 3 kips on the left, 2 things with 4 kips. Then at the separation between aluminum and brass, 2 things of 2 kips going to the left at the separation between brass and copper, and on the copper end, just 1 kip going to the left. That does put us in equilibrium, so just checking that out just to make sure that it's not moving anywhere. And our 3 different things, aluminum, brass, and copper, all do have different diameters. This is probably the most awkward thing on the planet to try and create. Why would you do this? Who knows? But just for the sake of creating all of these different little axial force deformation things that we want to calculate, we're going to have to see all the different variables we could use. So what we want to do is we want to find the deformation, obviously, from A to D. So again, step number 1 is to draw that axial force diagram. So, and it doesn't have to be anything, magically perfect. As far as the way of drawing this diagram goes, yes, you should try to make it as pretty as possible. But if it's not very clean, like my picture is not very clean, it's not going to be the end of the world. So again, axial force diagram, we have positive, that's tension by the way, and then we have negative, and that's compression. Our units are going to be in kips. And now what we're going to do is, again, in case you don't remember it, we need to make a cut between every change in load. So there's a change There's 3 kips, and then all of a sudden there's 2 things of 4 kips. So somewhere within this green band, we need to actually make a cut. So I'm going to do green here, and we'll just make a cut right there. Sorry for axing through all my numbers here, but there we go. Normal force always acts away from the cut, and in case you don't remember, we do need to cover up everything on that one side that we're not looking at. So there I literally just have 3 kips going to the left and a normal force N going to the right. I'm going to have to erase that eventually, but anyway, you're going to see that the normal force is 3 kips going to the right. Now to make sure that you get your signs correct, don't just go, force going to the right means that therefore it's a positive value. It's whether or not the normal force is acting away from the face. And in this case, yes, the normal force would be acting away from the face, so therefore we have a positive 3 kips in tension for our axial force. The next one we're going to cut is going to be, we'll do a light blue one here. So we need to look at between this load and the next change in load, which is the end of brass. So somewhere in that area, it doesn't really matter where, that's where we're going to make our cut. So I'm just going to cut right here just to try and screw up a lot less stuff. And again, we need to pick a side, either side, left or right. I'm going to continue to cover up everything that's over here onto the right. So again, don't look at that side when you do your free body diagram. And our normal force is going again away from the cut. If you're looking at this, we have 8 kips going to the right. We have 3 kips going to the left. Therefore, N needs to be going 5 kips to the left. And that going to the left does mean towards the face, and towards the face is going to be in compression. So we're going to be down here at -5 in compression. So moving on to the next one, we've got another change in load. Actually, we'll just leave it red. It's going to be somewhere in this copper one, right? Between the 2 things of 2 kips going to the left and the 1 kip that's also going to the left. That is a change in load, so we do need to make a cut in there. So because of that, we'll use red this time. Gonna make a cut just right here. You can pick either side, the left or the right, and truthfully, this time I'm actually going to pick the right side. So I'm going to cover up all of this stuff. Don't look at it. Don't look at any of that stuff. And remember that our normal force does go away from that face. So when you sum the forces in the x direction, you have 1 kip going to the left, and you just have N. Because of that, N's going to be 1 kip going to the right. But going to the right does mean that it is going to be going into the face, and into the face again does mean negative. So there we have 1 kip going in compression. So again, just to kind of clean this up a wee bit, I'm going to try and erase some of these things just so we can see our diagram again. So there we go, nice and beautiful. We have our axial force diagram. That's step number 1. Step number 2, we probably also want some values for, say, modulus of elasticity. That would be nice. I'm going to come over here and we'll put them in, we're running out of pretty colors. How about pinkish? So we're going to have the modulus of elasticity of aluminum, and it's very simple. Especially if you're doing problems out of a textbook, definitely look at what the textbook is going to use. So we're using the Hibbler books, so definitely make sure to figure out what Hibbler uses for those values. If not, otherwise just Google, and you're going to find that the modulus of elasticity of aluminum is 10,000 KSI. Obviously pay attention to your units. Don't put things in gigapascals if we're using US customary units. The modulus of elasticity for brass, same thing, different material. We're going to get 20,300 KSI. And lastly, the modulus of elasticity of copper is going to be 16,000 KSI. If you're wondering where I got these from, I literally just used Google. So again, these may or may not be the same ones that Hibbler uses because they do fall within a range. These may not be the ones that Hibbler uses for the textbook, so do keep in mind that you should actually look that up. It would probably be a nice idea to actually calculate some areas, right? So we have area of the AB portion, and that was a diameter of 5. So that's going to be pi over 4 times d squared. right? So I'm just going to kind of rifle through these. When you have 5 inches squared, you get 19.6 inches squared for AB. For the BC region, where you have brass, you're going to have pi over 4 times 8 inches squared. That'll be 50.3 inches squared for the area. And lastly, for C to D, in the copper region, we have pi over 4 times 4 inches squared, and that's going to be 12.6 inches squared for the area. Now again, remembering that our equation for deformation is P times L over A times E. What I have is P, right? I'm going to highlight my forces. Here's 1, here's 2, here's 3. So I have my 3 forces. Lengths. Let's find lengths. Here's length. We have 1.5 feet, 2 feet, and 3 feet. We have area. I'm just going to highlight it in orange because here's our areas. And then we have modulus of elasticity. And here we have modulus of elasticity. So we have all of our things, but they're constantly changing values. Like almost every single value actually is changing. So all we need to do is kind of plug and chug individually. So the deflection for A to B, we have P. P here is a green 3, so it's positive 3 kips. Do keep the positive or negative with it because this is going to make sure that you're doing either expansion or contraction, and those are expansion is positive, contraction is negative. So if you keep that with your force, it's really easy to keep track of whether this value should be positive or negative at the end. Our length we do have up there in purple, and our length is going to be 1.5 feet. But nobody should be talking about feet when they're talking about deformation, because measuring deformation in terms of feet is really ridiculous. So let's kind of change that to 12 inches in 1 foot, and magically that'll cancel out the feet, and we'll get inches. Then divided by the area, which is in orange over there, the area for AB is 19.6 inches squared. And lastly, E for aluminum, which we have as 10,000 KSI. So what did we get from all of this? We get 0.000276 inches. So cool, same thing, different numbers. That's all we're doing. One more time. We're going to find the deflection from B to C. This is in the brass region now, right? So for the brass region, it looks like our load, if I look above us, we're at -5. So -5 kips. Then we have a length, and our length, that purple length there, is now 2 feet. So 2 feet, and again, we don't like feet, we got to turn that to inches, so 12 inches in 1 foot. Divided by our area now for brass in the BC range, which was 50.3 square inches. And lastly, our modulus of elasticity for brass, which was 20,300 kips per square inch. So yes, you can watch all the units canceling if you want, but as long as you keep them all in the same set of units, everything will be great. And because we do have this negative over here, we are actually going to get a negative value. So we have negative 0.000118 inches. These are very small numbers, but I mean, that's kind of to be expected. Lastly, for the CD range, that's the copper range. And in the copper range, we look at our axial force diagram. We see that we're at -1. So -1 kip now for the force. The length did get even longer. Yep, now we're at 3 feet, even though my drawing is not to scale. So 3 feet, again, changing that to inches. 12 inches in a foot. Divided by the area for CD, which is 12.6 inches squared. And then lastly, the modulus of elasticity. The modulus of elasticity for copper, we said, was 16,000. KSI. Ta-da! So what are we actually going to get again? Because we have that negative in the front, we are going to get a negative value. So we have negative 0.000179 inches. And you might notice that I leave like a little gap in my numbers here, and that's just to kind of help you see how many zeros there are. Do it every 3 in kind of like the same way you would a comma. And anyway, if you want to find the total, we just have to sum them all up. So we're going to sum together 0.000276 minus, technically it's plus the negative, so we're going to get minus 0.000118, and then minus 0.000179. All that's going to be in inches. So what we're going to get for our total deformation is negative. It has a lot of zeros, so I'm just going to go ahead and try and move it to something that looks a little bit reasonable. So it's negative 21, but it's times 10 to the negative 6 inches. Ta-da! So there you have it. We have change in force, we have change in length, we have change in area, we have change in material. You can change anything you want, and anytime that there is a change, even if like the load doesn't change but the material changes, you do have to evaluate it every single time. So your load could be the same, but your material would be different, then you'd have to change it. Your load could be the same, the material could be the same, but the area could be different. You'd have to do another little segment. So for every segment, depending on which one of those 4 well, I mean, L can't really change, but based on if any one of these 3 starts changing, you make a new segment, and then you just sum it up for all the segments. So hopefully this isn't a very complicated topic.